to the pipe, vena contract to the pipe. The head loss due to contraction is mainly due to the flow changes or flow moving from vena contract to pipe. That is the reason head loss due to contraction takes place. Right? The flow changes from vena contract to small pipe. Right. Now we are going to derive the equation for the head loss due to contraction. This is one minor loss. Right now, already we have derived head loss due to enlargement. That formula is, this is the dia of the pipe. The dia of the pipe gradually increases or suddenly increases here. This is section 1.1. This is section 2.2. Already we have derived because of the expansion. The dia enlarged, or because of the expansion, head loss due to expansion is equal to V1 minus V2 square by 2G. This is at section 1.1. This is at section 2.2. V1 is the velocity at section 1.1. V2 is the velocity at section 2.2. Head loss due to contraction is because of the flow changes from the flow moving from section CC to section 2.2. Right? Now, based on this diagram, the head loss due to contraction HC is equal to cross-sectional velocity at vena contract is VC, velocity at section 2.2 is V2. Okay, velocity at vena contract VC, velocity at section 2.2 VT. Therefore, VC minus V2 square, VC minus V2 square divided by 2G. Here V1 is the section 1.1, V2 is the section 2.2. But in case of contraction, VC is the velocity at vena contract, V2 is the velocity at section 2.2. Right? This is the formula we have. Now, this equation can be written as HC is equal to VC into V2 by V2, there is a no change, multiplication, division, minus V2 whole square divided by 2G. Right? This is equal to V2 square by 2G taken out. Now, VC divided by V2 minus 1 whole square. Same equation I have written like this. HC, head loss due to contraction, is equal to V2 square divided by 2G taken out from this, VC by V2 minus 1 whole square. This is the relation we have. Right? Now, that is equal to HC is equal to V2 square by 2G, VC by V2 minus 1 whole square. Now, we want to determine the head loss due to contraction. Now, here we are going to apply the continuity equation at vena contract and at section 2.2. Right? This is the already I have given. This is section 2.2. This is vena contract. Right? At vena contract, AC is the cross-sectional area at vena contract. VC is the velocity at vena contract. A2 is the area at section 2.2. V2 is the area at section 2.2. Right. Now apply continuity equation at vena contract and section 2.2. Right. Continuity equation, what is the formula? A1 V1 equal to A2 V2. Now A1 V1 means at the vena contract, that is equal to AC VC is equal to at section 2.2 A2 V2. This is the continuity equation. From this equation, VC divided by V2 is equal to A2 divided by AC. Right? This is the relation we have. From this equation, AC VC is equal to A2 V2, or VC divided by V2 is equal to A2 divided by AC. But we know one relation, that is coefficient of contraction CC is the ratio of area at vena contract to the area of the pipe. Coefficient of contraction CC is equal to area at vena contract divided by area of the pipe. Okay, now here, therefore, coefficient of contraction CC is equal to area at vena contract divided by area at section 2 to A2. Right, CC is equal to AC by A2, or 1 by CC is equal to 1 by coefficient of contraction is equal to A2 divided by AC. Are you clear? Coefficient of contraction is equal to area at vena contract divided by area at section 2 to, or 1 by CC is equal to A2 divided by AC. Now, in place of A2 divided by AC, we are going to take 1 by C. Right? A2 divided by AC, we are going to take 1 by C. Therefore, velocity at vena contract divided by velocity at section 2 to is equal to, that is equal to A2 divided by AC. This is equal to A2 divided by AC is also nothing but 1 by CC. Therefore, in place of VC by V2, we are going to take 1 by CC. Right? Therefore, head loss due to contraction HC is equal to V2 square by 2G. In place of VC by V2, we are going to take 1 by CC. 1 by CC minus 1 whole square. This is the formula for the determination of head loss due to contraction. HC is equal to V2 square by 2G, bracket begin 1 minus CC minus 1. V2 is the velocity at section 2 to, G is acceleration due to gravity, C is the coefficient of contraction. Now C value, coefficient of contraction in case of pipes is taken as, C is taken as 0.62. In place of CC, coefficient of contraction 0.62. Therefore, HC is equal to V2 square by 2G 1 by 0.62 minus 1 whole square. This is equal to, HC is equal to V2 square by 2G into 0.375. Therefore, HC is equal to, if they have given coefficient of contraction value, CC is equal to 0.62. This value substitute here. Finally, we have the head loss due to contraction is equal to V2 square by 2G into 0.375. Therefore, finally, HC is equal to 0.3750 V2 square by 2G. This is the formula for the determination of head loss due to contraction. If they have not given coefficient of contraction value, that is CC value, then we are going to take the head loss due to contraction HC is equal to, head loss due to contraction HC is equal to, in place of 0.375, 0.5 directly taken into V2 square by 2G. Head loss due to contraction is equal to 0.5 V2 square by 2G if they have not given coefficient of contraction value. If they have given coefficient of contraction value, that is 0.622, then we have the value of coefficient of contraction is equal to 0.375 V2 square by 2G. Right? Right. Another minor losses. This is loss of head at entrance of the pipe. Loss of head and entrance of the pipe, that is already I have given. This is the pipe connected to the water tank. The water entering into the pipe, this loss is known as loss of head at entrance of the pipe, that is given by formula. Loss of head at entrance is equal to 0.50 V square by 2G, where B is equal to V square by 2G bracket begin A by CC A minus small a minus 1 whole square. Here in this formula, V is the velocity of flow in the pipe, velocity of flow in the pipe. G is acceleration due to gravity. A is the cross sectional area of the pipe, that is equal to pi d square by 4. A is the cross sectional area of the CC is the coefficient of contraction, and small a is the this is say d1. Small a is the cross sectional area of the obstruction, that is small a is equal to pi d1 square by 4. Right, pi d square by 4 is the capital A, pi d1 square by 4 is